Back to ajspeller.com. In today's tutorial, we're going to revisit the sliding ladder problem. And just to recap, we have a 13-foot ladder that's leaning against a wall. The bottom of the ladder slides away from the wall at a constant rate of a half a foot per second. So this bottom piece here is sliding away from the wall. We want to figure out how fast is the top of the ladder. This here is the top of the ladder. How fast is the top of the ladder sliding down the wall when the foot of the ladder is 5 feet away from the wall? Alright, through our calculations, we saw that the top of the ladder is sliding down at a rate of negative 524 feet per second. So what we're going to do now is we're going to actually model this problem with a graphing tool. So let's begin by using this equation here, x squared plus y squared equals 13 squared. So let's just write that in. X squared plus y squared is equal to 13 squared. Well, this here is the equation for the Pythagorean theorem. If we want to try to find the lengths of sides, it's also the same equation for a circle. In this case, it's a circle centered at the origin with a radius of 13. Also, from the problem above, we saw that dx dt was a half a foot per second. And notice that this half a foot per second is a constant, so the bottom of that ladder is moving along at a constant rate. What we're going to do now is, using this information, we're going to parameterize this equation for a circle. We're going to begin by saying that x is equal to t. Well, if x is equal to t, then that means we can rewrite this equation as t squared plus y squared is equal to 13 squared. And what we want to do now is we actually want to solve for y. So to solve for y, we need to subtract t squared from both sides. So here we have y squared is equal to 13 squared minus t squared. And to get just the value of y, we take the square root of both sides. And we see here that y is equal to the square root of 13 squared minus t squared. Alright, before we move on to the graphing tool or the modeling tool, we need to take into account the change in x over time. Currently we're saying that for each time unit, the x value is only moving over one place, but we want it to move over a half a foot per second, or a half unit per second. So in this case, we're going to say that x is equal to 1/2 t, or as a decimal we can say 0.5 t. So with that, we're going to change this equation here to show this change in x. So the new equation is going to be y is equal to the square root of 13 squared minus 0.5 t, and that quantity is squared. So this equation here and this equation here is what we're going to put into our modeling tool. So let's go ahead and do that now. Alright, once in the modeling tool, we're going to make this as dynamic as possible, and we're going to do that by using these tools here called sliders. So I'm going to select the slider tool, and I'm going to place a slider here, and this first slider I'm going to call the ladder. Alright, I'm going to give that ladder a minimum length of 1, and I'm going to give it a maximum length of 25, and I'm going to let it increment in tenths. I'm going to create another slider tool. And this slider tool I'm going to actually call dx dt, because it's going to allow us to dynamically change the rate at which the bottom of the ladder is sliding away. So we'll give it a minimum value of 0, and again a maximum value we'll say of 25, and again I'll increment that in tenths. And then for our last slider, this slider here is going to be for the time. So we're going to give this a time. We'll label it time. We're going to give it a minimum of 0, and here we're going to give it a maximum of what I'm going to call ladder divided by dx dt. And I'm doing that so that this here can be dynamic, and I'm going to let that increment in tenths, and I'm going to explain that here in just a moment. Alright, let's go back and just explain that. We know that the formula for distance is equal to the distance, well, one of the formulas is distance is equal to rate times time. Well, the distance here is actually going to be a length, and that length or that distance is going to be the bottom, or it's going to be the ground as the ladder is laying. So Once the ladder is laying flat, in this example, we know the ladder is going to have a distance or a length of 13. So here D is going to be 13. We said the rate at which the ladder is moving across. We said here dx dt is 1/2, and we're trying to figure out the time in this particular equation. So we have 13 is equal to 1/2 t. Well, to isolate for t, we're going to multiply both sides by the reciprocal of 1/2, which is going to be 2/1 on the right hand side, and multiply by 2/1 on the left hand side. These here cancel because I have 2 in my denominator, 2 in my numerator, so I end up with just t. This 13 is understood to be over 1, so I have 2 times 13 to give me 26, which is over 1, which is still just 26. So here, by us using that equation where I'm taking the length of the ladder, which I said was 13, and then I'm dividing it by the rate, I figure out how much time it takes for that ladder to lay flat. And that's what we did. Let's go back here. And that's what we did with the max here. The length of the ladder divided by the rate at which it's going, the rate at which the bottom foot of the ladder is sliding, and that's going to tell us how much time it takes for it to lay flat. All right, now what we're going to do is we're going to model the ground. So to do that, there is a function in this tool called curve, and it's going to allow us to put these parameters that we just figured out. So we're going to use the first one here. The first expression is going to be for x, and we're going to use 0.5 t, and I don't want the y value to move, so that's going to be 0. The parameterized variable is going to be time, which is the slider that we're using, and actually this here should also be time because the parameter we're using is the slider. It's labeled as time, so each one of these have to be labeled time. The starting value is going to be 0, and the end value is going to be the same expression I used before, which is going to be the ladder divided by dx dt. Alright, and so that we can see that, let's close this here. Let's go ahead and change some of the properties here. First, let's go to color. Since it's the ground, we're going to label it, or we're going to give it a color of green here. And what I want to do is let's change the thickness. Let's make it really thick. And right, that's all I want to do here. And let's go ahead and change the name. So instead of calling it A, let's call it ground. Alright, and also just to model what's going on, let's move this. Let's change the ladder length to 13, which is what we have in the problem. Let's change dx dt to 0.5 again, which is what we have in the problem. And notice how that's dynamically moving as I'm making those changes. And when I move the time here, we see that, well, we can't see yet what's going on, but we will be able to see in just a few more steps how the time is going to be impacted here. All right, next let's go ahead and let's add in the wall. Again, I want to use this curve function in the tool, and the first value I want to keep the x values at 0, keep those independent of the y values. And we said the y value that we're going to use is the square root. And what we want is 13 squared. Well, 13 squared is the length of the ladder. So to make that dynamic, I'm going to write ladder squared, and 0.5 is the dx dt, and t is for time, and then that quantity is squared. So let's put this in. So I have ladder, which again is going to be this value here, currently set at 13. I'm going to square it. Then I'm going to subtract off the dx dt value, so dx dt times the time, and I'm going to square that. The parameter variable is going to be time, the start value is 0, and again the end value is going to be the ladder divided by dx dt. And let's change the name of this from ground to wall, and let's also change some of the properties here. Let's make the wall's color, let's make it orange like it's leaning up against the brick wall. Let's make the line, and let's make it thick so that we can easily see what we have going on here. So at this point, we've got the wall and the ground drawn in. We have our two equations here for just the ground and just the wall. Now let's combine these two together, and I'm going to call those two the sliding ladder. So let's use the curve function again. I want the first option. This time I'm going to use the x value, which we saw is going to be dx dt times time, which we have up here. Dx dt we see is 0.5. That's why this is showing 0.5. Down here it's also going to show 0.5. The y value here, we're going to use this expression, which is the square root of the, not going to type in 13, we're going to use the variable ladder squared, and again we're doing that so that this can be a dynamic model. We're going to subtract off, again it's going to be dx dt, which is going to be the 0.5 times the time, and we want to square that. The parameter is going to be the time, which is this here is going to be again one of the controls here. The start value is 0, and the end time is going to be the length of the ladder divided by dx dt. Alright, and like I said earlier here, that this here is the equation for a circle, which is also the Pythagorean theorem. We've parameterized it, and by parameterizing it, we're limiting how much of the circle is being drawn. So here we're just drawing the first quadrant of the circle that's centered at 0, and again has the radius of 13, and we see that here. All right, next thing we want to do, whoops, let me go ahead and rename that. I'm calling this sliding ladder. Next thing I want to do is I need to take the derivative of the sliding ladder so that I can get the velocities for the top portion that's sliding down and the bottom portion that's sliding to the right. So here I'm going to use derivative. I'm going to go down and select curve. Press enter. The curve that I want is the sliding ladder, which is one we just created. All right, and it draws in the sliding ladder, and what we're going to see is that those rates are going to be shown down here. Again, they're in the negative region because the top of the ladder is going in a downward motion. And if I were to show the closer in on the graph, we see it is moved over at 0.5. We don't need to see that for what we're doing right here. We're going to create a label for that. So, matter of fact, let's turn off the quarter circle and let's turn off the velocities for right now. And the next thing I want to do is I want to place dots or points for that symbolize the top of the ladder and going to symbolize the bottom of the ladder. So what I'm going to do is I'm going to type in, we called it ground, so I'm going to type in the word ground, and I want to know the ground at this current moment in time. Whoops. And you know what, I think I need to capitalize. I think it's case sensitive, so let's try that in capital ground. Alright, and that's the ground at time 0, and then we're going to put in the wall at time 0. Alright, and what I'm going to do, I'm going to style these, and we see the wall here at time 0. So let's go ahead and stylize both of these. Let's see, A is one at the bottom, so this one at the bottom is moving to the right. So let's go to style, let's change the pointer to an arrow pointing to the right, and let's change the size. And then let's go ahead and select the wall. Oops, let's do this up here. Select the wall. Oh, it's not letting me do it like that, so let's just right click on it. So let's right click on the wall, go down to object properties, go to style, and let's change that to an arrow pointing down, and let's make it large so that we can see what's going on. Let's close this, and now let's slide the time across, and we can see that we've got some action here showing what's happening as we're progressing in time. We see the top of the ladder, which is point B, moving down. We see the bottom of the ladder, point A, moving to the right. Alright, to make this look a little better, let's go ahead and use something called segment. And I want the segment to go from a point to a point. I want it to go from point A to point B. So now we have that in place. Let's go ahead and label that, instead of letter F, let's label that ladder. and I want to change the style of the ladder. So let's go here to, well, let's do color, and well, let's just do color actually. So color to give it a nice red color, and style, let's make it thick like we made the other items there. Let's go ahead and close the properties, and again, let's move this back and forth. All right, and we've got some pretty good a pretty good model going here. For A and B, let's also allow us to see more of the information. Let's go to object properties again. Let's see, for the label, I want to show the name and the value. Let's do the same thing for the wall. Go to those properties. I want to see the name and the value. So now when we look at this, we see that, all right, the wall, that the top of the ladder is currently at 10.25 feet, and we see here that the bottom of the ladder is 8 foot from the wall. All right, let's put in some labels so that we can see the values for the rate of change of the bottom of the ladder and of the top of the ladder. So let's go here, and we want to see, let's do fraction text, and the text that I want to grab the x value, so I'll place an x from the sliding ladder velocity, so let's type that in, at a particular moment in time. And then I want to do the same thing. Whoops, was that sliding ladder? Nope, I want to get that for the velocity. So I need to use the prime, the little apostrophe for prime. Alright, now that's what I'm looking for, because this here represents dx dt, which is a half, which is what we know it should be from the problem. So I got the half there, and what I want to do now is let's go ahead and add on, matter of fact, let's go ahead and do the second one for the top of the ladder sliding down. So I want to use fraction text. I want to grab the y value from the sliding ladder velocity, so I place the prime at a particular moment in time, and that there signifies what that rate is. In this example here, what we see currently is at the moment that we're 8 feet from the wall, we see that we're moving down, that the top of the ladder is moving down the wall at this particular rate. Let's go ahead and clean that up a little bit. Let's add in, so that's the rate. Let's add in the units, and let's just say we have feet per second. Let's do the same thing up here, feet per second. And then let's look at the properties here so that we can, let's come here and let's clean that up a little bit so it looks a little bit better. So let's use the it's the latex formula or latex formula, backslash fraction, curly brace for the numerator, a second set of curly braces for the denominator. I want feet in the numerators, I want seconds in the denominators, and in the front for this one, this is for y, so I want to add in, let's paste that in, and I want to do this for dx, I'm sorry, actually dy dt. Whoops, and let's press OK, and then let's pull this over. Let's get rid of these properties. Let's pull this over, so this here is for, that there is for dy dt, and let's do the same thing for dx dt. So I've got that already in the buffer, so let's go ahead and paste that in there. Let's come here, and actually, you know what, let's add an equal sign in here too. So equals, and this here should be dt, and this here should be dx, and again we know it's dx because we're grabbing the x value there. And then let's pull this up so that this is sitting there. Oops, actually let's move this down, let's move that there so it snaps in. Let's let that one snap in. Let's come back here, let's place in the equal sign. Whoops, I want the equals in here to make that look better. And what I want to do is I want to fix the object and absolute positioning, fix the object and absolute positioning. Alright, so now as we slide the time back and forth, we see it moving up and down. We see our change in rate for the y-axis, or the top of the ladder. And what I want to do now is let's go ahead and just do this problem. Let's slide this back, and we can zoom out. Well, actually, we'll keep it like this. We'll move this down some. And in this problem, we wanted to know when the bottom of the ladder was 5 feet from the wall. We wanted to figure out what this rate is. So let's go ahead and move this along the timeline. Again, we know this first number here signifies the number of feet from the wall. So let's go back until that's 5. Alright, that there is at 5, and we see that our calculations are the same. We have negative 524 feet per second. That's the same thing we got from here. And just notice, as I was saying earlier, we can dynamically change the length of the ladder. We could dynamically change the rate at which things are, the bottom of the ladder is moving, and of course we can change the time, and we see it moves accordingly. So let's move this back to 5/10. Let's move this back to 13. And one other thing I want to show is that we can actually have this animating on its own. So let's go here to time. Let's go down to object properties. I don't want it to oscillate. Let's just have it forever increasing. We can close that, and let's go here to play. And then here we see that our work is actually animating for us here. Pretty cool. What I want you to notice as well, before we wrap up, is that the bottom is moving at a constant rate, and we see that the top is moving at an ever increasing rate. Really slow to start, but then it really starts to pick up speed, and like around here we see it pretty much slam into the ground. Alright, that sums up this tutorial by ajspeller.com. Hope you enjoyed it. I enjoyed making it. Please send us any comments on these tutorials, and as always, thank you for watching.